Good morning students. Today we will be studying the conformational analysis. Conformational analysis is nothing but it is the study of energies of different spatial arrangement of the atoms. Here we will be rotating the bonds so that you will get different conformations. So study of the energies of those different conformation is nothing but your conformational analysis. Here first we will study the conformational analysis of ethane. First molecule we are taking the example of ethane. That is we will study the conformational analysis for ethane. We know that the formula for ethane is CH3CH3. That is C2H6. You know that the formula for ethane is C2H6. How you can represent this? That is two carbon atoms with 6 hydrogen atoms. You have first carbon atom with 3 hydrogen atoms and second carbon atom with 3 hydrogen atom. Represent this molecule in the form of Newman projection. You will be having the front carbon atom with 3 hydrogen atoms and back carbon atom with 3 hydrogen atoms. In the Newman projection, you have to represent in the Newman projection. So you will be having front and back carbon atoms with the 3 hydrogen atoms each. Here in ethane, you observe two types of conformations that you are calling as eclipsed conformation and staggered conformation. You have two types of conformations, that is staggered conformation and the eclipsed conformation. Staggered conformation is the one wherein the diagonal angle is 60 degrees. Diagonal angle is 60 degrees. Diagonal angle is also called as a torsional angle. Diagonal angle is nothing but the torsional angle. How you can define this dihedral angle means it is the angle between two atoms, that is two bonds, angle between two bonds which are originating from two different atoms. How you are defining? It is the bond between, it is the angle between two atoms, or you can say two bonds which are originating from two different atoms or from two different planes. For example, see here, this is your first hydrogen atom of front carbon and second that is first hydrogen atom of back carbon atom. If you are referring the first hydrogen atoms, refer the first hydrogen atoms for both the carbon atoms. See here, the angle between these two bonds or these two hydrogen atoms is called as a dihedral angle. You are calling this as a dihedral angle because these bonds are originating from two different atoms, that is from front carbon atom and back carbon atom. So this angle is called as a dihedral angle, and in this case the dihedral angle is 60 degrees. In the case of staggered conformation, the dihedral angle is 60 degrees. Whereas moving to the second conformation, that is it is called as a eclipsed conformation. This is eclipsed conformation wherein the dihedral angle is 0 degrees. Again see here, these are the first hydrogen atoms of the two carbon atoms. There is no angle between these two hydrogen atoms. For example, see here, you have two carbon atoms. Here both the hydrogen atoms will be eclipsed or lined up. Means like this. If this is a front carbon hydrogen atom, if this is a hydrogen atom of the second carbon atom, both will be lying like this. Means they will be parallel to each other. That we call as eclipsing. That we call as eclipsed or lined up hydrogens. So the angle between them will be 0 degrees. That is dihedral angle. That will be 0 degrees. Why? Because they will be parallel to each other, or we can say they are eclipsed. So the dihedral angle will be 0 degrees. And when compared to this staggered conformation, this eclipsed conformation is less stable. Why? Because there is a steric strain between these two hydrogen atoms. Here in the staggered conformation, you observe less steric strain. Why? Because the hydrogen atoms, they are lying apart from each other. They are far away from each other. So compared to this eclipsed conformation, staggered conformation is having less steric strain between the bonds, whereas eclipsed conformation is having more steric strain. You observe more steric strain in the eclipsed conformation. Why? Because the two hydrogen atoms are nearer to each other. They are lining upon each other, and there you observe a repulsion between the electrons in the bonds. There is a repulsion between the electrons in the bonds. So because of this reason, eclipsed conformation is less stable when compared to the staggered conformation. Staggered conformation stable and it is having less energy, and eclipsed conformation is having more energy and it is less stable. See here, you have to draw the energy level diagram for the conformational analysis of ethane. In the y-axis, we will be taking energy in kilocalories per mole. On the x-axis, we will be taking dihedral angle. This dihedral angle can be represented by either pi or omega or theta. You can represent the dihedral angle by these three symbols. You can represent by these three symbols. So on the x-axis, we will be having dihedral angle. Since we have the rotation, that is dihedral angles 0 degrees and 60 degrees. In the similar way, you have to take the difference in such a way that you get 0, 60, 120, 180, 240, 300, 360, so on. So write the conformations according to their energies and stabilities. See here, we have staggered conformation at the dihedral angle 60 degrees. See here, 60 degrees here. You are writing the staggered conformation over here. Write the staggered conformation, that is first conformation here. This is your first conformation which is having less energy. On the y-axis you have energy. So at the lower energy level you have to represent the staggered conformation with the dihedral angle 60 degrees. Whereas the eclipsed conformation you have dihedral angle 0 degrees. This you will be observing here. Here you are having the eclipsed conformation with the dihedral angle 0 degrees. Again you can represent this here. Eclipsed conformation can also be represented here. Why? Because the dihedral angle between these two atoms can be 120 degrees. Why? Because once you rotate the bonds, you will be getting the dihedral angle 120 degrees. See here. You will be getting the dihedral angle 120 degrees. So you can write this over here. Means, see here, for example, you have hydrogen atom here. We are referring these two hydrogen atoms. For example, if you are referring these two hydrogen atoms, once you rotate the 60 degree angles, this hydrogen will be coming over here. This hydrogen comes over here. So the dihedral angle will be 120 degrees. The dihedral angle will be 120 degrees. So you can write the conformation here. You can write the conformation here. And as well as you can write the conformation, eclipsed conformation here with the 0 degree dihedral angle. And the energy difference between these two conformations is 3 kilocalories per mole. Here you also get the second conformation, that is eclipsed conformation. The difference between these two conformations, that is eclipsed and staggered conformation, is 3 kilocalories per mole. It is 3 kilocalories per mole. It is also called as energy barrier. That is, energy barrier between these two conformations is 3 kilocalories per mole. If you write in the form of joules, it will be 12 kilojoule per mole. If you are writing in the form of kilojoule, the energy difference will be 12 kilojoule per mole. It will be 12 kilojoule per mole. So this is a conformational analysis of ethane. The next conformational analysis we have for the butane, that is conformational analysis of butane. You know that the formula for butane is CH3, CH2, CH2, CH3. You have 4 carbon atoms, that is first, second, third and fourth carbon atom. So for this molecule you have to write the Newman projections. You have to write the Newman projections. Here we are taking these 2 carbon atoms as the front carbon atom and back carbon atom. The front carbon atom is bonded to 2 hydrogens and 1 methyl group, whereas the back carbon atom is also bonded to that is 2 hydrogen atoms and 1 methyl group. Here we are taking the methyl groups as the substituents. We are considering the methyl groups as the constituents for these 2 carbon atoms, for the front and back carbon atoms. So for this molecule you have to write the conformations. Here in the butane you will be observing 4 conformations. You are observing 4 conformations. Out of 4 conformations, 2 conformations will be eclipsed conformation and the other 2 conformations will be staggered conformation. Whereas in the ethane you have 1 staggered conformation and 1 eclipsed conformation. But here in the butane totally you are observing 4 conformations. Out of 4 conformations, 2 conformations are the eclipsed conformation and the other 2 conformations will be staggered conformation. So these four conformations will be differing from each other relative to the methyl substituents. That is relative to the position of the methyl substituents. Here we are taking the methyl groups as the substituent. These four conformations, they are differing from each other by the relative positions of the methyl groups. See here, the position of the methyl group is changing in all the all the conformations. Means we are rotating the molecule. We are rotating the molecule, or we can say we are rotating the bond. We are rotating the bond to get different conformations of the butane. This difference is only because of the position of the methyl groups. We are differing the position of the methyl groups. Means we are rotating only the bonds related to the methyl substituents. So here you observe four types of conformations. Two are eclipsed and two are staggered conformations. See here, the first conformation we have is a syn periplanar. It is called as a syn periplanar and it is fully eclipsed. This first conformation and the third conformation, these two conformations are the eclipsed conformation, and this second and fourth conformation, these two conformations are the staggered conformations. Totally you have four conformations, two eclipsed conformation and two staggered conformations. Out of that, the first one conformation we have is a staggered, that is eclipsed conformation. It is called as a syn periplanar. It is fully eclipsed, that is the dihedral angle will be 0. The dihedral angle will be 0. See here, this is front carbon atom. The methyl group of the first that is front carbon atom and the methyl group of second carbon atom, that is back carbon atom, they are lining upon each other. They are eclipsed on each other. So the dihedral angle will be 0 degrees. It will be 0 degrees. This means that both the that is methyl group are repelling each other. That is electron in the both the bonds. Electrons in the bonds, they are repelling each other. As a result of that, you will be observing more steric strain. You observe more steric strain here. And it will be less stable conformation. Why? Because there is a more steric strain between the two methyl groups. The electrons in the bonds will be repelling each other. As a result of this conformation, that is first conformation, is less stable. So if you rotate these bonds, that is methyl bonds, to 60-degree rotation, we are rotating it to the 60 degrees. See here, we are rotating this bond, so it will be coming here. See, it results in the second conformation. We are rotating the molecule, or you can say rotating the bond. So this methyl group will be coming here. We are rotating. Since we are rotating only 60 degrees, the bond will be here. The methyl group comes here. This conformation is called as a gauge conformation. It is called as a gauge conformation. G-A-U-C-H-E. It is called as a gauge conformation, and it is also called as synclinal. It is also called as synclinal. Here the dihedral angle is 60 degrees. See here, we are referring only the methyl groups. We have to refer any of the two groups. Don't change the groups. Here we are referring the two methyl groups. So the dihedral angle between these two methyl groups is 60 degrees. It is 60 degrees, and this is called as a staggered conformation. Why? Because the two referred methyl groups, they are far away from each other. When compared to the first conformation, they are far away from each other, and there will be a less steric strain between the methyl groups when compared to the first conformation. See, again rotating 60 degrees, you will be getting the third conformation. See here, this is your methyl group. Again in rotating this, you will get the methyl group here. You will be getting the methyl group here. So the dihedral angle between these two methyl group will be 120. It becomes 120. So the dihedral angle for this conformation will be 120 degrees, and it is called as anticlinal, or it is also called as partially eclipsed conformation. It is also called as partially eclipsed conformation. Why? Because the dihedral angle is not 0 here. You are not having fully eclipsed conformation. Fully eclipsed conformation means the dihedral angle will be 0 degrees. So this is called as partially eclipsed conformation or anticlinal conformation. Here the dihedral angle will be 120 degrees. So compared to this, that is compared to the second conformation, this will be more stable. Why? Because the two methyl groups are far away from each other. They are far apart from each other when compared to the second conformation. So moving to the fourth conformation, again rotating this to 60 degrees, you will be getting the CH3 group over here. CH3 group over here. So first CH3 group, that is front carbon atom methyl group is here, and the second carbon atom, back carbon atom methyl group comes over here. So the dihedral angle will be 180 degrees. See here, the dihedral angle becomes 180 degrees. That is, it is called as anti-dihedral angle. It is called as anti-dihedral angle. That will be 180 degrees. It will be 180 degrees. This conformation is also called as anti-periplanar. It is also called as anti-periplanar conformation, wherein the dihedral angle between the two methyl groups is 180 degrees, and this is more stable when compared to all the conformations. Why? Because the two methyl groups, they are far away from each other when compared to all the conformations. They are far away from each other, so there will be very less steric strain between the two methyl groups. There will be very less steric strain between the two methyl groups. So if you write the stability order between the eclipsed conformation and staggered conformation, see, staggered conformation, you have two staggered conformations and two eclipsed conformation. See here, first and third are the eclipsed conformation. One is a fully eclipsed conformation, another one is a partially eclipsed conformation. So out of these two eclipsed conformations, the third conformation is more stable than the first conformation. The third conformation with the dihedral angle 120 degrees is more stable than the first conformation with the dihedral angle 0 degrees. Why? Because the two methyl groups lies far away from each other in the third conformation. So you observe less steric strain. It is having lower energy and more stable when compared to the first conformation, wherein the two methyl groups, they are lining upon each other. As a result, there will be a more steric strain and more repulsion between the electrons in the bonds. So this becomes less stable with the more energy. This is about two eclipsed conformations. So moving to the staggered conformation, that is the fourth and the second. These two are the staggered conformations. So write the stability order between these two conformations. See here, in the fourth conformation, two methyl groups, they are lying away from each other, far away from each other. So there is very less steric strain between the two methyl groups. So fourth conformation will be more stable than the second conformation. When compared to these two conformations, that is fourth one and the second one, that is gauge conformation and the anti-conformation. Anti-conformation is more stable than the gauge conformation. Why? Because in the gauge conformation, you have more steric strain when compared to the anti-conformation. So fourth conformation is more stable than the second conformation. That is, anti-conformation is more stable than the gauge conformation. This is a stability order for the four conformations. So moving to the energy level diagram. Again, in a similar way, you are taking on the y-axis, that is energy in kilocalories per mole. On the y-axis, again we are taking energy in the kilocalories per mole, and x-axis we are taking the dihedral angle. Again here we are rotating only 60 degrees. So take the 60 degree difference. It will be 0, 60, 120, 180, 240, 300 and 360, so on. So that is, designate all the conformations according to their energies and stabilities. First conformation, see here, it has the dihedral angle 0 degrees. It has dihedral angle 0 degrees. Here is 0 degrees here. So here we will be writing the first conformation, that is fully eclipsed conformation. You have first conformation over here. It is having higher energy, so represent at the higher energy level and at the 0 degrees. And it is having 4.5 kilocalories per mole, that is 19 kilojoule per mole energy difference. From the lower energy level, it has 4.5 kilocalories per mole, or you can say 19 kilojoule per mole energy difference. So moving to the second conformation, that is Gauge conformation, you have the dihedral angle 60 degrees. So for the 60 degrees, and it is having less energy when compared to the first conformation. So write the second conformation over here with the 60-degree dihedral angle. Your second conformation will be coming over here with the dihedral angle 60 degrees, and the energy difference or energy barrier will be 0.9 kilocalories per mole. The energy difference will be 0.9 kilocalories per mole. Next, moving to the third conformation, that is anticlinal, or you can say partial eclipsed conformation. The dihedral angle is 120 degrees. See here, at the dihedral angle 120 degrees, we are representing the third conformation. We have the third conformation over here. When compared to this second conformation, this is having more energy. So represent it over here at the higher energy level, and the energy difference will be 3.8 kilocalories per mole. The energy difference will be 3.8 kilocalories per mole. And the last conformation you have to represent is antiperpendicular, or you can say anti-conformation. Here the dihedral angle you have is 80 degrees, that is 180 degrees. So represent this fourth conformation at the 180 degrees. This is your 180 degree. So you have fourth conformation over here. You have a fourth conformation over here. We are representing it to the lower energy level. Why? Because compared to all these conformations, compared to all these three conformations, this is more stable with the lower energy. So we are representing at the very lower energy level when compared to these three conformations. So it is represented at the lower energy level when compared to these three conformations, because it is more stable with the lower energy level. So write the fourth conformation over here, and it will be more stable when compared to all the conformations. So this is about the conformational analysis of butane and ethane. The next example we have is that is conformational analysis of cyclohexane. First we have studied the example of ethane, then butane, and last we have that is conformational analysis of cyclohexane. Here Bayer strain has given two models for the cyclohexane, that is two conformations for the cyclohexane. The first conformation is a rigid conformation, or you can say rigid form. First form is a rigid form. It looks like a chair, so it is named as a chair form. It is named as a chair form. The first form, or you can say the first conformation of cyclohexane, is nothing but a chair conformation. It is a rigid form. Its shape is like a chair form, so it is called as a chair form, or you can say chair conformation of the cyclohexane. The second conformation of cyclohexane, it looks like a boat and it is flexible. It is a flexible form. We can say the flexible form of the cyclohexane is nothing but a boat form. The second form is a boat form. The conformation looks like a boat, so it is named as a boat form. So for cyclohexane, you have two conformations, that is one is a chair form, the second one is a boat form. So let us see the conformations and their stabilities and energies. The first conformation we have is a chair form. The first conformation of cyclohexane is chair form. Here this is your chair form of cyclohexane, and we are writing it in the form of Newman projection. See here, you have 6 carbon atoms and 2 CH2 groups. Here in the Newman projection of the chair form of cyclohexane, all the bonds, you can see all the bonds. There are hydrogen bonds, that is bonds which are bonded to hydrogen, that is bonds from the carbon is directly bonded to hydrogen, as well as for the CH2 groups. By this diagram, or you can say projection formula, you can understand that all the bonds in the Newman projection or in the chair form, they are staggered. All the bonds are staggered. So as a result of that, there will be a minimization of the strain. We can say that the steric strain will be minimized in this Newman projection of chair form. That is, in the chair form, all the bonds, since all the bonds in the form are that is staggered, as a result of this, there will be a minimization of the steric strain between the groups, or you can say between the bonds. So as a result of this form, chair form becomes most stable form of the cyclohexane. You can say the most stable form of the cyclohexane is nothing but the chair form. Why? Because all the bonds are staggered and there will be a less steric strain between the bonds. So because of that reason, we can say chair form of cyclohexane is the most stable form. And moving to the second conformation or second form, that is, you say it as a boat form. The second form of cyclohexane, that is conformation of cyclohexane, is boat form. Here the boat form of cyclohexane, we can say it is less stable when compared to the chair form. Why? Because see the diagram here, these two hydrogen atoms, these are called as inner hydrogen atoms, or you say it as a flagpole hydrogens. Flagpole hydrogens, or you say it as a inner hydrogens. These two hydrogen atoms are called as flagpole hydrogens or inner hydrogens. These two hydrogen atoms, they are closer to each other. As a result of this, they will be interfering with each other. This results in the steric strain. That is, it causes the steric strain. As a result of that, there will be instability for the boat form when compared to the chair form. Why? Because these two hydrogen atoms, that is flagpole hydrogen atoms, they interfere with each other, causing more strain between the that is hydrogen atoms, or we can say there will be a more strain in the molecule. This leads to instability for the boat form when compared to your chair form. So by this we can say this boat form is less stable. It is less stable and having high energy. And see here, you have eclipsed form of the Newman projection. Here all the bonds, either you can say the bond which is bonded to the hydrogen, or you can say CH2 group, all the bonds are eclipsed. That is, they are lying about each other. As a result, all the bonds between all the atoms, or you can say between all the electrons in the bonds, there is a repulsion, resulting in the strain between the molecule. As a result of this, there will be a less stability for the boat form when compared to your chair form of the cyclohexane. So here, this boat form is, it can be converted into another form, or we can say it can be stabilized. This boat form of cyclohexane can be stabilized by doing or by following one method, that is, see here, these are your flagpole hydrogens. When you move apart the flagpole hydrogens, you can get the stability in the boat form. So how you have to do, or how you can make apart the hydrogen atoms, that is, you have to take these four hydrogen atoms, that is the hydrogen atoms bonded to the third carbon atom, second carbon atom, sixth carbon atom and fifth carbon atom. Considering these four hydrogen atoms, that is bonded to third, second, fifth and sixth carbon atoms, you have to hold that is third and second carbon atom in one hand and fifth and sixth carbon atom in another hand, and you have to twist the molecule in such a way that the molecule, you will be getting this molecule, that is, first it will be like this. When you hold the second and third molecule in one, that is carbon atom in one hand, and fifth and sixth carbon atom in another hand, and you have to twist the molecule in such a way that the fifth and second carbon atom goes upward and the third and sixth carbon atom come downward. So this results in another form which you are calling as a twist boat form. It is called as a twist boat form. Since we are twisting the carbon atoms, that is these four carbon atoms, fifth, sixth, third and second carbon atoms, we are twisting these four carbon atoms In order to get a stable form of the cyclohexane, that is stable boat form of cyclohexane, which is known as a twist boat form. While compared to the boat form, your twist boat form is more stable and it is having less energy. Why? Because when you twist these carbon atoms, that is when you are twisting this third, second, fifth and sixth carbon atoms, these flagpole hydrogens here, these are the two flagpole hydrogens. In the boat form, they are nearer to each other, or we can say that they are interfering with each other, causing the strain in the molecule. But when you twist these four carbon atoms, see here, your flagpole hydrogens, they are moving apart. They are moving apart from each other. So this reduces the strain in the molecule and it leads to the greater stability of the twist boat form when compared to your boat form. So comparing these two forms, you can say that the twist boat form is more stable while compared to your boat form. Twist boat form is more stable when compared to your boat form by we can say that is 5.5 kilocalories per mole. It is stable by 5.5 kilocalories per mole, and this twist boat form is less stable when compared to the chair form by 23.4 kilocalories per mole. We can say that among these three, chair form is most stable conformation or most stable form. Then twist boat form is more stable when compared to this boat form by 5.5 kilocalories per mole, and this twist boat form is less stable when compared to the chair form by 23.4 kilocalories per mole. The energy level diagram for the conformational analysis of cyclohexane is here. On the y-axis again you have energy in kilocalories per mole, that is in kilocalories per mole, and on the x-axis you have conformations. Here we are not taking dihedral angle, we are taking the conformations because we are twisting the carbon atoms. Here we are not rotating the bonds, we are only twisting the carbon atoms. So here on the x-axis we are taking the conformations. See here we have a chair form, then boat form, then twist boat form. The first stable conformation at the lower energy level, your lower energy level is here. You are getting the chair form conformation because it is having less energy and it is more stable. And this chair form conformation is when it is you are moving the carbon atoms, it will be getting another transition state conformation. You call it as a transition state conformation, that is called as a half chair conformation. It is called as a half chair form by moving the carbon atoms, that is second carbon first, second, third and fourth in the plane, and fifth carbon above the plane and sixth carbon below the plane. That is by moving the first, second, third, fourth carbon atoms in the plane and fifth carbon atom above the plane and sixth carbon atom below the plane, you will be getting the twist, that is transition state conformation. By moving the carbon atoms in the chair conformation, that is first, second, third, fourth in the plane and fifth carbon atom above the plane and sixth carbon atom below the plane, by moving those carbon atoms you will be getting the twist, that is transition state conformation, which is called as a half chair form. You call it as a half chair form or you call it as a half chair conformation. Moving to the other conformations, that is you are getting the twist boat conformations, or you can say twist boat forms. Here these twist boat forms are at the lower energy level and they are more stable when compared to this boat form, and they are less stable when compared to your chair form. Why? Because chair form is having that is all the bonds here are eclipsed, whereas in the twist boat form the bonds are eclipsed. Sorry, in the chair form they are staggered, whereas in the twist boat form they are eclipsed. As a result of that, you can observe more strain in the twist boat form when compared to the chair form. So as a result of this, when compared to chair form, your twist boat forms are more stable, and the energy barrier between chair form and twist boat form is 5.5 kilocalories per mole. You have energy barrier that is 5.5 kilocalories per mole, whereas the energy barrier between your chair form and half chair form forms, that is half chair form and chair form. Completely chair form is 10 kilocalories per mole. So after one twist board form, you will be getting the complete board form. It is also a transition state conformation. It is also called as a transition state conformation. And this transition state conformation is separating these two twist board forms, and moving from twist board form to, again we will be getting another transition state conformation, which is nothing but a half chair form. It is also called as a half chair form, and moving from this half chair form we will be getting, finally we will be getting the cyclohexane, that is chair form of cyclohexane. See here the energy barrier between the half chair form and the chair form of your cyclohexane is 6.9 kilocalories per mole. It is 6.9 kilocalories per mole. So this completes your conformational analysis of the three molecules, that is